Today we're going to revisit a topic that you were introduced to earlier in this course, correlation, and we're going to introduce a parametric inferential test known as linear regression. If you remember, correlation examines relationships between variables. It's useful to determine if a relationship exists and if that relationship is statistically significant. Correlation is used in exploratory research to observe what variables might have impacted the results of a statistical test. We display correlation with a small italicized R. It's a quantifiable interrelationship or association between two variables. For example, BMI and percent body fat are associated with each other. As percent body fat goes up, so does BMI. But that's not the only reason that BMI might increase. A person could have a high amount of muscle mass. This would also have an increase in BMI. BMI is also impacted by height. The correlation coefficient measures the strength of a relationship between two variables. The higher the correlation, the more the two variables have in common. Perhaps you remember this slide from Chapter 5 as well. Independent variables can be positively associated with dependent variables. They can be negatively associated, or two variables could have no correlation whatsoever, as you see in the graph on the right. A negative correlation will have a negative value for R. This is sometimes called an inverse correlation. When values are positively correlated, the R will be a positive number, and this is sometimes called a direct correlation. When the R is equal to 0, we know that the two variables are not correlated at all. Sometimes data can be curvilinear. For example, we know that obesity rates in children are lowest at extreme poverty and extreme wealth. So looking at our last graph there on the right, if our x-axis was a predictor, you could see how it correlates with the y-axis in a curvilinear fashion. A Pearson's R of 0, as I said, was no relationship, and a Pearson's R of +1 or -1 equals a perfect correlation, neither of which occur with any frequency in real life. You may remember this slide as well from Chapter 5, where we provided the equation for calculating the Pearson's R. We also provided an SPSS output that looked like this. You see that we compared jumping distance and height. We see that they are significantly correlated, where R is 0.777. And we were glad that SPSS did the work for us of that very laborious statistical calculation from the equation. Once we get our R value, we can interpret it as follows. So, the correct method to report correlation from our previous example: there was a strong positive correlation between height and jumping distance, where R was 0.77, the number of observations was 27, and our p-value was 0.00. Let's go through the process of testing a correlation coefficient. We must first meet the assumptions for this calculation. We must assure that the sample that we've drawn is representative to the population to which we plan to infer our results. We must also assure that our variables are of normal distribution, and we must meet the assumption of homoscedasticity. In other words, our variables for x and y must have equal variances. We also want to have some idea that the variables that we're correlating are related somehow to each other in a reasonable way. We would not expect BMI and IQ to be correlated, but we might expect BMI and height to be correlated. When we look at the data requirements for making comparisons, we need to assure that we have 2 variables per subject. The data may be any level, but we may have to select special types of correlations depending on the level of measurement. For continuous data, we use the Pearson product R. But let's say that I wanted to compare nominal level data to interval level data. I would use point by serial. Going back to our earlier examples, we could see if patients who were on a branched chain amino diet, and that would be yes or no, nominal level, was correlated to ammonia levels in their blood, and that would be interval level data, and so we'd use a point by serial statistic. What about ordinal level data? What if we wanted to see if there was a correlation between, let's say, income rank and BMI rank? We would use the Spearman's coefficient. Note that SPSS treats these the same. When our data are interval level, both of them, we'll use the Pearson's R, such as blood glucose and A1C. There are situations where you can't use any type of correlation. This table gives you an idea of when you can use it and when you can't. Basically, if you're dealing with a categorical value that has more than 2 categories, you can't run a correlation. For example, race, diagnoses, grade in school, correlations are not an option. Let's say we want to know if there's a correlation between fall risk and hemoglobin level. We're going to use hemoglobin as a surrogate marker of anemia or degree of anemia. Both variables will be treated as ratio level data. And we write our hypothesis. The research hypothesis says there will be a relationship, and our null that we will test says there will be no relationship between fall risk, and that's going to be our dependent variable, and hemoglobin level, our independent variable. This is a non-directional correlational test. We set our level of significance, and we compute the value of R. We find that it's 0.182. This is a weak relationship, but is it significant? We can compare our obtained value for this correlation to the critical value needed to reject the null if we have a sample of 60 comparisons. So our degrees freedom is 58 since we're looking at 60 subjects from 2 different groups. Using the table on page 362 of your book, we see that the critical value needed to reject the null at 0.05 significance with 58 degrees freedom is 0.25 for a two-tailed test, again a non-directional test, of significance. Since our obtained value is less than our critical value, we fail to reject the null. There is no significant relationship between fall risk and anemia, where R with degrees freedom of 58 is equal to 0.182 and our P is less than 0.05. We can estimate how much of the variance of one variable explains the variance of the other with the coefficient of determination, or we square the R. So if we square the Pearson's R in our previous example, we see that 0.182 squared is 0.033. Only 3% of fall risk is explained by hemoglobin levels. That means fall risk in this hospital must be due to something else. Maybe it's pain medication. Maybe it's diagnosis. Maybe it's something subtle, such as the distance patients have to travel in the facility. Or maybe it's acclimation time. How long have the patients been there? We might expect that patients who are new to the facility and unfamiliar with the surroundings might fall more than patients who've been there for the full 21 days. The bottom line is that correlation does not infer causation, and correlation will not explain all the variance in a model. Therefore, Correlation should be reported in terms of strength, direction, and significance. Now we've just looked at a by hand method of calculating and interpreting a correlation. Let's use SPSS to run a correlation and interpret the printout. Using a data set that you're familiar with, we will test and see if our skin fold method of estimating percent body fat or calculated BMI. These are the steps that we will go through. We will select Analyze, Correlate, and since we're looking at two variables, bivariate, and we're going to move, make sure we've got the right variables here, percent body fat using Slaughter's equation into the box, and we need to put calculated BMI in here. Let's find that. We could produce a statistics table, but we won't in this case. Make sure that we select a two-tail because we wrote a non-directional hypothesis. And we can let SPSS give us a clue as to whether or not this is significant. And we run our results, and we'll go back and offer an explanation. So we see our correlation here. R is 0.847 and it is significant at the 0.01 level for a two-tailed test. So we correctly write our results. There is a significant, strong, positive correlation between Slaughter's skin fold method of estimating percent body fat in children and a calculated BMI, where R with 319 comparisons is equal to 0.817 and the P is 0.000. So we reject our null. Sometimes it's helpful to create a graphic when we are attempting to understand relationships between variables in a correlation. These are the steps to creating a scatter dot. And we'll do that now for you. We will select Graphs, Legacy Dialogues, Scatter Dot, Simple, and now this is the, if you go back to the first part of this where we made an issue out of what goes on the X and Y axis, we're going to move calculated BMI to our y-axis because what we're trying to observe is, can our skin folds be sort of a predictor of the person's or the child's calculated BMI? We will move the percent body fat using Slaughter. Not it. There it is, to the x-axis, and we can give it a title. Nothing there we need to be concerned with. And select OK. And we get an idea that as a child's percent body fat increases, so does their calculated BMI. There's a little clue we can do too. We can edit. And we can add a fit line. See if that's the right. Yes. Apply, close. This will be important to you a little bit later, but this is a goodness of fit line for the data. So if we go back to our SPSS, or I'm sorry, PowerPoint, this scatter plot tells me quite a bit. It says that there appears to be a good, strong, positive correlation between the two variables. Typically, we would run this first, and then we would conduct our actual printout. But this scatter plot tells me something else that the SPSS calculation does not. Notice that the variables tend to be more correlated, much closer together, here where the children are at more of an ideal weight. When we get out here to the very heavy children, there's a lot more variability. So that's important. We look at the R square, 0.718. This is pretty good. It's telling us that the coefficient of determination lets us know that this is a good line of fit between these two variables. The more the independent variable explains the dependent variable, the higher this coefficient of determination is going to be. And it's getting pretty close to 1, so that's good. If there's a decreased relationship between x and y, the data points will be located far away from the fit line or the regression line. This means that there's large error in the model. The two variables are not related. If we had run a fit line for hemoglobin and fall risk, we would not have seen a cluster so close. So as I said, in the previous example, our model is actually quite good with an R square of 0.718. Almost 72% of BMI is explained by percent body fat using Slaughter's equations. Of course, that leaves 29% not explained, but at the end of the day, using skin folds with Slaughter's equations isn't a bad option for assessing anthropometrics in children, especially since if that's all you've got. So I'd feel pretty comfortable using the Slaughter method to make conclusions about percent body fat in this population of children. I might feel less confident about it in our larger children in the sample. You may also remember this particular slide from an earlier presentation, a correlation matrix. This is where we can look at more than one comparison at a time. It's still a bivariate comparison, but we're simply doing multiple comparisons. So correlation gives us an idea if the variables in our model are related and the nature of the relationship. The correlation coefficient tells us the percentage of variance in one variable that's accounted for by the variance in the other. But neither tells us if our model or our sample matches the population. We used inferential statistics to compare our sample results to the population. Z-test, t-test, and Anova. We will use correlations to move us to a different kind of inferential statistical test, prediction. Linear regression, or prediction, utilizes the relationship between the independent variable and the dependent variable to predict the score of the dependent variable from the independent variable. Let's say that again a little more slowly. When two variables are related, it's possible to predict a score on one variable from their score on a second variable because the relationship is linear. The goodness of fit line that we saw in this presentation can be used to develop a prediction equation. Now, the equation looks like this. Our outcome variable is equal to the intercept plus the slope times a predictor variable. y prime is equal to beta times x times, added to alpha, or our coefficient constant. Linear regression answers this question. What is the value of one variable given the value of another variable? It's used to predict the value of one from another. We can predict unknown or future events based on current data, and it's a very powerful tool. As nurses, you've probably used this type of statistical judgment many times. For example, a patient comes in and they've not had anything to eat or drink in several days. They're at 70% of their ideal body weight. Their respirations are low. Their temperature is low. Intuitively, you know that all these variables are correlated with a high mortality rate. We actually, in the healthcare world, have developed different kinds of predictor tools. Maybe you've read about them in your nursing texts. Things like Ranson's criteria, Apache, Bali. All these are methods of determining severity of different kinds of diseases, such as liver failure or pancreatitis. Here are the assumptions of regression. The sample is of normal distribution. It's drawn from the normal population. We meet the criteria of homoscedasticity. The variables have to be scale. Although there are linear regressions that can test nominal level data, this is called logistic regression, and we will not cover that in this class. The variables are related in a linear manner. Here's our research hypothesis. There is a prediction of y, that's our dependent variable, based on the value of x, our independent variable. In a real-life situation, we could say, there is a prediction of calculated BMI based on Slaughter's equations for percent body fat in children. The null hypothesis that we test is, there is no prediction of y based on the value of x, or there's no prediction of calculated BMI based on Slaughter's equations for percent body fat in children. If we further explain the formula, y prime is the predicted score of y for a given value of x. I hope that in your mind you are visualizing the graph where we had a y-axis and an x-axis. Beta is the slope or direction of the line. It's also referred to, and I would highlight this, the regression coefficient. It's the rate of change in y with 1 unit change of x. Our next value is the point at which the line crosses the y-intercept if x is 0, and x is the value or score that's being used as the predictor. It's our independent variable. I wanted to illustrate the regression constant here. We said it's the y-intercept, or the value of y when x is 0. This is where the regression line crosses the y-axis. Notice it can be positive or negative. Pay special attention to what we call this value. It's called the regression constant. Further dissecting our equation, the beta or slope, this is called the regression coefficient. Now this terminology is going to be very important when we look at an SPSS output file. So beta or beta weight or slope, regression coefficient, these are all the same thing. So in order to use the value of x to predict the value of y, we must first use the data to construct a regression line. If you have a really good memory and you go back to one of the very first lectures that I posted, we said that we can take statistics and infer to the population, or we can take a sample and use that data sample to make an inferential line. And now we're doing that in regression. So our beta slope is defined as the rate of change in y for each 1 unit change in x. The larger the slope value, the greater the change in y. Positive or negative values for beta, when beta is positive, y increases as x increases. When beta is negative, y decreases as x increases. Knowing this direction can help you interpret your results. The regression line, or beta, is our model that tells us how well our data fit reality. We need to be sure that the line or model really is the best line. Is it the line that goes through or hits most of the data points in a correlation? If we have a good line or model, we can predict approximate height based on age, as we see in this example. So what we're trying to tell you is we want to make sure that when we compute a beta, that it really is the line that would intersect most of the points in a correlation. Now SPSS will check this for you by conducting a separate Anova. Even though we find the very best line possible, there are going to be data points that do not touch that line. These are residuals. They represent the degree of error in a regression line or fit line. The line of best fit minimizes residuals or error as much as possible. How do we know that this is a line that best fits it? We use Anova, or method of least squares. We sum all the distances between each data point. Perhaps you remember this from our previous lecture. The smallest sum of squares provides the best fit line or regression line. So when we do regression, we calculate beta weight, and then we run an additional test to make sure that this line is the best line. It's called the sum of squares residual. Let's go through an example. Perhaps you can appreciate how this regression line or slope is calculated. We'll also see how to calculate the regression constant. We want to use age as a predictor of systolic blood pressure in women. We enter age and systolic blood pressure on 10 female subjects, and from this data we want to develop a prediction equation. We compute the slope using the equation that's presented here. Then we compute the regression constant alpha. With the red arrow that you see here, this is where the regression line will cross the y-axis. Now, for any given value of x, in this case any woman's age, we can predict the value of y, or what her systolic blood pressure might be, using this brand new equation that we've generated from our data sample. So let's go back. This is our regression equation. And in this particular case, our y is equal to a beta weight of 64.3 plus 1.39 times some number. With our regression equation, we can predict the systolic blood pressure of a 38-year-old woman as y equals 64.3 plus 1.39 times 38, which is equal to a systolic blood pressure of 117. Now, what are the chances of a random 38-year-old woman having a systolic blood pressure of 117? If we were to stop 100 women on the street and ask them their age, which would be taking a big risk, and predict their systolic blood pressure using this equation, would we be right every time? No, of course not. Data points are rarely so perfectly correlated where r is equal to 1. We know there is error in our model. What we need to know is, how good is our model? How can we be sure our model is a good one? SPSS will test our model or our regression line using the Anova. The Anova will tell us if our model is better than just using an average. In other words, of these 10 women, what was the average systolic blood pressure? Can we go through life and say, well, of all women, their average systolic blood pressure is, let's look back on our table here, and we found that the average systolic blood pressure was 137. Can we just use the mean, or can we use the regression line to predict it? Again, Anova will tell us if our line is a good fit. SPSS will calculate the sum of squares total, the sum of squares residual, and the sum of squares of our model. The important point to remember, if the model results in better prediction than using an average, we expect the sum of squares of our model to be greater than the sum of squares of residual or error. You've seen this all before. You know how to calculate mean squares using the sum of squares. Thankfully, in this course, SPSS is going to do it for us and produce an Anova. The F statistic is the proportion of the mean squares of the model, in other words, what our model explains or our fit line, and the residual, or the amount of error in our model. Here's the important point. This is where I wish I had a drum roll. If our Anova is large, then we have little error. If we have a very small value for F, then we have a lot of error. The data points are located far away from the line. So perhaps our regression line is not a good predictor. The takeaway, big F, good model, good prediction. Small f, not a very good predictor. Now, just because we have a good fit line or a big value for the f doesn't mean it explains everything. SPSS will also produce for us the coefficient of determination, which we saw before. We're now going to go through an SPSS output and interpret all of these different things that the software will calculate for us in a regression. But before we do that, I need to tell you one thing. When we went over descriptive statistics, we talked about how important it would be to run those before we did any type of inferential statistics. And that is very true in terms of regression. Outliers can greatly impact regression. Remember that we made box plots, or you can do a stem and leaf to find out if there is a variable that could impact the error in your model. And I would refer you to those lectures as far as how we handle outliers in a sample. Main thing is that you want to take care of them because they can certainly impact the residual error in your model. Alright, so let's go through an SPSS. We're going to use a different example than the one that we computed by hand. Let's say we want to know if science achievement scores of 12th graders can predict their math scores. This is what we'll get when we run a regression in SPSS. 3 different tables that we just described for you. We get a model summary, which is our coefficient. It will generate an Anova to tell us if our regression line is good, and then it will actually tell us the coefficients that go into our predictive equation. The first piece of information that we get from regression is the model summary table. This tells you how much of the variance the predictor variable explains in the dependent variable. It's our correlation squared, and we see that it's 0.516. So our correlation, these two are very well correlated, and as far as its predictive value, in other words, how well one score can predict the math score, the science predicts the math, it's 0.516. So there's obviously some other things that are at play here. The amount of variance explained is the R square. The next thing that we get is the Anova Table. Remember I told you SPSS will make sure or run a test of your regression line to see if it's really good, if it's a good model. Can we trust our regression equation? It tests to see if our model is a better predictor than just using the mean or average test on an achievement score. You'll notice that SPSS gives you the sum of squares both for the model and the error. In this example, we have a large F, so that's a pretty good model, and it is significant. In other words, there's a big difference between the model and the error, and we want it to be that way. This means our regression line is good. The third chart are going to be our coefficients, what we can use to plug into an equation where one predicts the other. Remember, y prime is equal to beta times x times plus the y-intercept. So here's our beta, here's our y-intercept. This is probably one of the most important pieces to remember as you begin to interpret your regression output. We can use this information to predict a student's math achievement simply by plugging these values into the equation of the line. Math achievement is equal to 20.131 plus your beta times science achievement score. In other words, a 1-unit increase in science achievement results in a 0.66 unit increase in math. So I could use this. If I was a high school teacher and a student earned a certain score on their science test, I could plug it into this equation and predict what their math score would be even before they take the test. If we wanted to actually predict the y or dependent variable, we plug in a particular science score and see what the equation would predict our math score would be. Let's say that a student scores 75 on a science test. We would predict that their math score would be a 69.6. In real life, we're less concerned with predicting a particular value. We're more interested in how the y prime changes as our independent variable changes. So we might want to know, how does math achievement score change when there's a 1 unit increase in math achievement? We just use the variable coefficient. So we would say that for every 1 unit increase in science achievement, there is a 0.66 unit increase in math achievement. There are other types of regression. Multiple regression occurs when we use multiple independent variables. It will give us multiple slopes. Multiple regression tests the ability of multiple independent variables to predict an outcome. For example, we could use percent body fat and percent muscle mass as a predictor of body mass index, or BMI. Multiple correlations are tested as well as each beta weight. There is one intercept constant alpha, but each independent variable has a separate beta weight or slope. Would we want to run a test of 5, 6, 7, 8, 9 different independent variables? Probably not. Most of the time, multiple regression will only use maybe 2 or 3 different independent variables. When using 2 independent variables as a predictor for a dependent variable, the 2 IVs should be correlated to the dependent variable but not to each other. For example, do years of education and years of work experience predict income? Years of education and years of work experience are really not related to each other, but they could be predictors of income. If 2 independent variables are related to each other, they can predict each other. This is a problem called collinearity. We can test for this problem in Spss using the variance inflation factor, or VIF, when we run a multiple regression. Generally, a VIF of 10 or more is a problem for the ability of one independent variable to predict another. There's also non-linear regression. It's called polynomial. Do you remember that curvilinear relationship I showed you earlier, where I gave you the example of weight in children and their socioeconomic status? This provides a prediction equation from data that's shaped like a polynomial or arc. It uses different equations to develop the prediction equation. It's always a good idea to create a scatter plot and fit line when you're eyeballing your data to see which type of regression statistic that you need to use. And that's the end.